To understand the profound shock German engineers experienced upon testing the Sherman tank, one must first comprehend the deeply ingrained engineering philosophy that governed German tank design. This was not merely a matter of technical specifications, but a cultural and doctrinal mindset, one forged in the fires of interwar theory and early blitzkrieg success. It was a philosophy that prized qualitative supremacy above all else, a pursuit of perfection that cast a long, formidable, and ultimately crippling shadow over the entire Panzerwaffe. This worldview would set the stage for their complete inability to comprehend the American approach embodied by the M for Sherman. The German engineering ethos was rooted in the concept of the Schwerpunkt, the point of maximum effort. Applied to tank design, this meant creating a weapon system that could achieve a decisive breakthrough by annihilating any enemy armor it encountered. The tank was not just a tool, it was a dueling weapon, an armored knight designed for qualitative single combat. This thinking produced machines like the Tiger I, which was less a mass-produced vehicle and more a rolling piece of artillery. Its primary attributes were immense: a massive 88mm kilowatt K-36 gun derived from the legendary flak cannon, and thick, heavy armor that made it nearly impervious to frontal attack from most Allied tanks at standard combat ranges. It was designed to dominate the battlefield from a distance, destroying enemies long before they could effectively respond. This pursuit of qualitative supremacy, however, came at a catastrophic cost. The Tiger was a masterpiece of over-engineering. Its interleaved road wheels provided a smooth ride but were nightmarishly complex to maintain. A single damaged inner wheel required the removal of multiple outer wheels to access. Its transmission and steering system, while advanced, was delicate and required highly trained specialists to repair. The tank was so heavy, at 57 tons, that it required a special set of narrower tracks for rail transport, which then had to be swapped out for combat tracks at the front, a laborious process involving a mobile crane. It was not a tank built for the mud, snow, and dust of the Eastern Front or the hedgerows of Normandy, it was a tank built for an ideal, controlled dueling ground. This philosophy extended beyond the Tiger to the very structure of the German armored force. German industry, with its artisanal traditions and focus on quality, produced a bewildering array of models. A single unit might operate Panzer IVs, Panthers, and Tigers simultaneously. While this provided tactical flexibility, it created a logistical apocalypse. Each tank had entirely different ammunition, engines, transmissions, tracks, and optical systems. A mechanic trained on a Panzer IV was not a mechanic for a Panther. A supply officer had to manage dozens of different, non-interchangeable part numbers for what was essentially the same function across different vehicles. This was their Panzer Zoo, a system that valued specialized excellence over standardized, sustainable efficiency. The doctrine supporting these machines was equally focused on the qualitative duel. German tank tactics emphasized engagement at long range, where the superior optics and high-velocity guns of their tanks could pick off opponents with near impunity. They trained to target the enemy's strength, his armor, and destroy it. This mindset conditioned the entire German military apparatus, from the general staff down to the junior officer, to judge a tank primarily by its gun caliber and armor thickness. A tank's value was measured in its ability to win a one-on-one engagement. It was from within this Tiger's shadow, this culture that worshipped at the altar of technical perfection and individual combat power, that the German engineers first examined a captured Sherman. They saw its 75mm gun, which seemed modest compared to the long 75 of the Panther or the 88 of the Tiger. They measured its sloped but comparatively thinner armor. They noted its taller profile. By every metric they had been taught to value, the Sherman appeared inferior, a crude and simplistic implement next to their finely honed scalpel. They were prepared to dismiss it entirely, to confirm their belief in American industrial mediocrity. They were looking for a dueling champion, and they saw what they believed was a mere brawler. They were about to discover that they had been measuring the wrong things all along. The shock would not be that the Sherman was a better dueler, but that it was playing an entirely different game, a game where reliability, numbers, and strategic mobility were the true keys to victory. The first encounters between German panzer crews and the M for Sherman on the battlefields of North Africa and later in Europe were not meetings of equals, but collisions of diametrically opposed military philosophies. To the battle-hardened veterans of the Afrika Korps and the Eastern Front, the Sherman initially appeared not as a peer, but as a testament to American naval and industrial clumsiness. This perception, fueled by battlefield experience and deep-seated prejudice, led to the swift and derisive christening of the Sherman with a nickname that would haunt it for decades, the Ronson, after the lighter whose slogan claimed it, "Lights first every time." This dismissal, however, was based on a superficial and ultimately fatal misreading of the American tank's true nature. The initial German assessment was rooted in the brutal metrics of tank versus tank combat. A German Panzer IV, particularly the later models with the long 75mm kilowatt K40 gun, or the terrifying new Panther, could engage and destroy a Sherman at ranges where the Sherman's own 75mm gun was ineffective. The Sherman's armor, while well sloped, could be penetrated by these high-velocity weapons with relative ease. German crews reported seeing Sherman tanks brew up with a dramatic and terrifying rapidity when hit in the ammunition storage, which was unfortunately located in vulnerable sponsons along the sides of the hull. This propensity to catch fire, a flaw that would later be addressed with wet ammunition stowage, cemented the Ronson reputation in the minds of both German and Allied tankers. It confirmed the German belief that the Americans built flimsy, dangerous death traps. This perception was compounded by the Sherman's tactical behavior on the battlefield. German doctrine, honed in the vast expanses of Russia, emphasized long-range gunnery and defensive positioning. They would often hold a reverse slope, using their superior optics to pick off advancing Allied armor from a distance. The Americans, by contrast, often employed the Sherman in a more aggressive, mobile role, using numbers and speed to close the distance. To the Germans, this looked like tactical incompetence, a foolish charge into the killing zone of a superior weapon system. They failed to see that this doctrine was enabled by the Sherman's mechanical reliability and numerical advantage. The Americans could afford to take losses to achieve a breakthrough, trusting that the majority of their tanks would complete the mission. The physical design of the Sherman also drew German scorn. Compared to the low, sleek, and menacing silhouette of the Panther or the Tiger, the Sherman was tall and, to German eyes, ungainly. This height was a deliberate design choice to accommodate a large turret ring, allowing for future gun upgrades and providing a more spacious and less fatiguing interior for the five-man crew, but it was interpreted as poor design. The simplicity of its construction, its large, cast or welded plates, seemed crude next to the intricate interlocking armor and complex machining of German tanks. It looked like a product of a factory, not a craftsman's workshop, and in the German military culture of the time, this was a mark of inferiority. Furthermore, German intelligence and propaganda had spent years cultivating a specific image of the American soldier and his equipment: soft, inexperienced, and reliant on material wealth rather than martial skill. The early performance of green American tank units in North Africa at the Kasserine Pass seemed to confirm this bias. When these units, poorly deployed and led, lost Shermans to more experienced German ambushes, it was seen as proof of the tank's inherent weakness, not the result of a complex set of tactical circumstances. The Ronson was, to them, the perfect vehicle for such an army, flashy and numerous, but ultimately fragile. This dismissive attitude was a profound and costly psychological error. By focusing exclusively on the Sherman's shortcomings in a head-on duel with their best heavy tanks, the German military establishment blinded itself to the tank's formidable strengths. They saw their fires but not the dozens of other Shermans that absorbed a hit, kept fighting, or were repaired and back in the field within days. They saw the tall silhouette but not the ergonomic interior that reduced crew fatigue and improved combat efficiency over long periods. They mocked its simplicity but failed to grasp that this simplicity was the key to its strategic power. The stage was set for a shocking revelation, one that would come not from a battlefield, but from the controlled environment of a testing ground, where German engineers would be forced to confront the uncomfortable truth that they had been judging a masterpiece of strategic design by the narrow and flawed standards of tactical dueling. The German dismissal of the Sherman, born on the battlefields of Tunisia and Normandy, began to curdle into a nagging, professional curiosity by 1943. Anecdotal reports from the front were contradictory. While Panzer crews celebrated their ability to destroy Shermans at range, maintenance officers and logisticians in the rear began hearing whispers of an enemy tank that rarely broke down, that could be fixed with a hammer and a wrench, and that seemed to be available for battle day after day after day. To the analytically minded German engineering corps, this was a paradox that demanded investigation. The myth of the Ronson needed to be tested against cold, hard data. The opportunity to do so arrived not with a bang, but with a near miracle: the capture of a pristine, completely operational M4A1 Sherman. The circumstances of the capture varied depending on the theater. In the fog of war, a Sherman might become isolated from its unit, bogged down in mud impassable to its recovery vehicles, or be abandoned by its crew after a minor mechanical fault that could not be addressed under fire. For the German testing program, the ideal specimen was one that had not been destroyed by combat. A tank gutted by an 88mm shell told them nothing they didn't already know: it was a wreck. What they needed was a living, breathing example of American engineering, a tank that could be driven, disassembled, and analyzed in its fully functional state. The process of securing such a prize was a military operation in itself. Once located, the abandoned Sherman would be guarded until a specialized recovery team could arrive. These teams, often equipped with heavy-duty German half-tracks or captured Allied recovery vehicles, faced the delicate task of extracting the tank without causing further damage. If it was bogged, they dug it out. If it had thrown a track, they reattached it. The goal was to get the tank moving under its own power, a testament to the robustness that had allowed it to be recovered in the first place. The sight of a perfectly intact Sherman, now sporting a hastily painted Borken cross, rumbling back to German lines was a strange and unsettling one for soldiers on both sides. The selected tank was then transported to a major testing facility, most notably the immense Wehrmacht Vehicle Testing Center at Kummersdorf, south of Berlin. Here, away from the distortions of propaganda and the adrenaline-fueled exaggerations of the frontline, the Sherman would be subjected to the same rigorous, methodical analysis that the Germans applied to their own prototypes and captured equipment. Kummersdorf was the inner sanctum of German military technology, a place where engineering dogma reigned supreme. To bring the Sherman here was to bring it before the high priests of the German technical faith. The initial external inspection at Kummersdorf both confirmed and challenged German prejudices. The engineers, clad in their spotless laboratory coats, walked around the tank, their notepads in hand. They noted the tall silhouette, the rounded cast hull of the M4A1 model, and the apparent simplicity of its construction. They tapped the armor and compared its thickness to their own schematics. Their first impressions likely aligned with the frontline assessment: this was not a Tiger. It lacked the brute force intimidation of their own heavy tanks. It looked almost ordinary. But then came the first moment of quiet revelation: the tank started. Not with the labored groaning and clouds of black smoke that often characterized cold starts for German tanks, but with a relatively quick, confident roar from its radial aircraft engine. The engineers would have noted the ease of the start, the accessibility of the engine compartment, and the straightforwardness of the controls. This was not the complex, temperamental beast they were used to. This was a machine that seemed designed to work, not just to impress. The stage was now set for the most comprehensive and humbling evaluation the Sherman would ever undergo. The German engineers, with their world-renowned thoroughness, were about to take the American tank apart piece by piece. They were prepared to document its every flaw, to catalogue its weaknesses, and to confirm their tactical superiority. They were not prepared for what they would actually discover: a philosophy of design so radically different from their own that it would force them to question the very foundations of their engineering doctrine. The capture of the pristine Sherman was not the end of their inquiry, it was the beginning of an uncomfortable education. The German engineers at Kummersdorf began their analysis with the quiet confidence of masters dissecting the work of a novice. They had their calibrated instruments, their detailed procedures, and a deeply ingrained belief in their own technical superiority. Their mission was to document the Sherman's shortcomings. But as they delved deeper into the tank's design, a disquieting realization began to dawn. The initial shock was not one of inferiority, but of profound philosophical dissonance. The Americans had not built a worse tank, they had built a different kind of weapon system altogether, one where the guiding principle was not complexity, but ruthless, elegant simplicity. The first shock came from the sheer accessibility of the components. On a German tank like the Panther or Tiger, opening an engine compartment was a major operation, often requiring the removal of heavy armor plates and the use of a crane. On the Sherman, the entire engine could be accessed by a few crewmen unbolting and lifting large, hinged panels on the rear hull. This was not a minor convenience, it was a revolutionary approach to maintenance. A German mechanic might need hours just to reach a faulty component. An American crew could perform the same task in minutes under battlefield conditions. The Germans documented this with a sense of bewilderment, noting how every major system, the engine, transmission, and final drives, was mounted for easy removal and replacement as a unit. This philosophy extended to the interior. The German engineers, accustomed to the cramped, demanding interiors of their own tanks, were stunned by the Sherman's ergonomics. The turret basket rotated with the gun, allowing the loader and commander to work efficiently without having to scramble over stationary floor obstructions. The controls were straightforward and logically arranged. There was space. For men who had spent hours in the claustrophobic, mechanically intense environment of a Panther, the Sherman's crew compartment felt almost luxurious. It was designed not just for fighting, but for enduring long campaigns without exhausting its crew. The next revelation was in the manufacturing. German tanks were masterpieces of machining, with components fitted to precise tolerances. The Sherman embraced a different standard, the tolerance for repair. Its parts were designed with clearances that allowed for dirt, grit, and minor wear without immediate failure. Where a German gearbox might be a complex assembly of finely machined gears, the Sherman's was robust, simple, and, crucially, interchangeable with those in other Shermans. The Germans took apart the tank's vertical volute spring suspension, VVSS, and noted its simplicity and resilience compared to their own complex, interleaved roadwheel systems, which were notorious for freezing solid in Russian mud and being nightmarish to repair. This simplicity was a direct assault on the German engineering ethos. The German mind valued the perfect, optimized solution. The American mind valued the good enough solution that could be reproduced 10,000 times and fixed by a 19-year-old soldier in a muddy field. The Germans documented the use of rubber block tracks on the Sherman, which provided a smooth ride and reduced wear, compared to their own all-steel tracks that chewed up their own road wheels and produced a deafening metallic clatter. They noted the standardized bolts and fittings throughout the vehicle, a stark contrast to the specialized, often unique fasteners used in German designs. Perhaps the most profound shock came from the electrical system. German tanks were labyrinths of complex, hard-wired electrical looms. The Sherman utilized a modern, centralized electrical system with junction boxes and standardized connectors. If an electrical fault occurred, a crew could isolate and replace a component rather than trace a single wire through the entire hull. This was maintenance logic applied on a systemic level, something the German engineers had to acknowledge was brilliantly effective, even if it offended their sense of intricate craftsmanship. As their analysis progressed, the initial derision turned into a grudging, then rapt attention. They were not looking at a primitive design, they were looking at a mature, fully realized philosophy of industrial warfare. The Sherman was not designed to be the best tank on the battlefield in a one-on-one duel. It was designed to be the most numerous, the most reliable, and the most sustainable tank on the battlefield. Its simplicity was not a flaw, it was its greatest weapon. It allowed for mass production on a scale Germany could not match. It allowed for rapid repair and a high operational readiness rate that German panzer divisions could only dream of. The engineers at Kummersdorf were forced to confront a terrifying truth: while they had been building exquisite, handcrafted dueling swords, the Americans had built a reliable, sharp, and infinitely replaceable bayonet. And in a long, bloody war of attrition, it is the bayonet, not the dueling sword, that ultimately wins. The heart of any tank is its powertrain, the engine that gives it life and the drivetrain that translates that power into motion. It was here, in the oily, mechanical core of the captured Sherman, that the German engineers experienced their most profound technical shock. They were prepared to critique an inferior power plant. Instead, they dismantled a system that represented a fundamentally superior approach to automotive design for warfare. The Sherman's powertrain was not just good, it was a miracle of reliability, serviceability, and strategic logic that laid bare the critical flaws in their own philosophy. The first element to undergo scrutiny was the engine itself. The particular M4A1 they tested was powered by the Continental R975 radial aircraft engine, a 9-cylinder, air-cooled power plant. To the Germans, this was an unorthodox choice. Their own tanks used liquid-cooled, inline engines specifically designed for armored vehicles. The radial design was compact, relatively lightweight, and phenomenally robust. The engineers noted with professional admiration its air cooling, which eliminated vulnerable radiators, hoses, and coolant, all common points of failure in their own tanks, especially in the Russian winter where coolant could freeze and crack engine blocks. The R-975 could withstand significant abuse and was known for running even when damaged. But the true revelation was the concept of engine interchangeability. The Sherman was designed from the outset to accept multiple different engines depending on manufacturing availability. This specific tank had a radial engine, but other Shermans rolled off production lines with the Ford GAA V8, or twin GM diesel engines. This was a logistical masterstroke that the Germans, with their rigid, single-engine designs for each tank model, found both brilliant and bewildering. It meant the American Army was not crippled by a shortage of one specific engine type. If Continental couldn't produce enough R-975s, Ford could pick up the slack with the GAA. This flexibility was alien to the German industrial system, which was plagued by production bottlenecks for their specialized tank engines. The drivetrain provided the next series of shocks. The Sherman's transmission and final drives were located in the front of their hull, a deliberate design choice. While this made the drivetrain more vulnerable to direct frontal hits, it offered an overwhelming maintenance advantage. The entire powertrain package, transmission, final drives, and steering units, could be removed as a single unit through the front of the tank after removing the armor cover. This was a repair that could be accomplished in a field workshop in a matter of hours. The Germans meticulously documented this process, their notes likely tinged with envy as they compared it to the ordeal of replacing the transmission in a Panther or Tiger, which often required the removal of the turret and was a days-long job for a fully equipped depot. This accessibility was a theme that ran through the entire automotive system. The steering levers were simple and direct, connected to a robust clutch and brake steering system. While less sophisticated than the controlled differential steering in later German designs, it was virtually indestructible and could be repaired by a crew member with basic training. The Germans tested the clutch assemblies and noted their long service life and ease of replacement. They saw how a damaged clutch could be swapped out without needing to remove the entire transmission, a common necessity in their own vehicles. The final drive units, which transferred power from the transmission to the tracks, were another point of admiration. They were heavily built, sealed against dirt and water, and designed for easy access. The Germans were acutely aware of the weaknesses of their own final drives, particularly on the heavy Tiger and Panther tanks, which were chronically underdesigned for the vehicle's weight and power. These components were a frequent point of failure, often stripping their gears under the immense strain and requiring a major overhaul. The Sherman's final drives, by contrast, were over-engineered for reliability. A conservative design choice that paid enormous dividends in operational availability. As the engineers ran the Sherman through its paces on the test track, the automotive miracle became undeniable. The tank started reliably in cold weather. It accelerated briskly. Its top speed was respectable. But its most impressive characteristic was its endurance. They drove it for hundreds of test kilometers, simulating the long road marches that were a reality of the Eastern Front. The Sherman did not break. It did not overheat. It did not throw a track every 50 kilometers like the fragile Panther. It just kept going. The conclusion was inescapable. The German engineers were looking at a powertrain that was not designed to win a spec sheet comparison on horsepower per ton, but to win a war. It was designed for mass production by automobile factories, not specialized armaments works. It was designed to be fixed quickly by average soldiers, not by master mechanics with doctorates in engineering. The automotive miracle of the Sherman was not a single technological breakthrough, but the perfect integration of robust, proven components into a system whose primary quality was not peak performance, but unwavering reliability. It was an engine and drivetrain built for the real world, and in the real world of mud, dust, and combat, it was proving to be far more effective than Germany's temperamental mechanical thoroughbreds. For the German engineers at Kummersdorf, the true revelation of the Sherman tank came not from their calibrated instruments, but from a simple, practical exercise, they handed the tools over to a group of veteran Panzer crewmen and asked them to perform basic maintenance and repairs. What followed was a masterclass in human-centered design that stood in stark contrast to the crew's daily reality with their own machines. The Sherman, they discovered, was not just engineered for performance, it was meticulously designed for the man inside it, transforming grueling, day-long chores into tasks that could be accomplished in minutes. The exercise began with a routine task, replacing a damaged road wheel. On a German Panther, this was a notorious ordeal. Due to the interleaved design, a single inner road wheel could not be accessed directly. To replace it, the crew first had to remove several outer wheels, a process requiring heavy jacks, specialized tools, and hours of backbreaking labor, often under the threat of enemy fire. It was a task universally dreaded. The German crew approached the Sherman with the same grim expectation. Their surprise was palpable. The Sherman's vertical volute spring suspension, VVSS, featured individually suspended bogies. A damaged wheel could be unbolted directly. There were no interleaved wheels to remove. With a standard wrench and a jack, the crew swapped the road wheel in under 30 minutes. The engineers documented their astonishment. This was not a minor improvement, it was an order of magnitude reduction in labor and exposure time. A task that could immobilize a Panther for half a day was a minor interruption for a Sherman crew. Next, they simulated a track repair. On German tanks, track links were heavy, complex, and connected with pins that were often seized by mud and required sledgehammers and brute force to drive out. The Sherman's T-41 track, with its center guides and simple, sturdy pins, was dramatically easier to work with. The crew, using standard-issue tools, was able to break the track, remove a damaged link, and reassemble it in a fraction of the time it would take on their own vehicles. The simplicity was breathtaking. The German crewmen, their hands raw from years of wrestling with seized track pins, looked at the Sherman's system with a mixture of disbelief and envy. The engineers then directed the crew to the engine compartment. They presented a simulated fault, a failed fuel pump. On a German tank, accessing the fuel pump could involve draining fluids, removing ancillary components, and contorting into impossible positions within the cramped engine bay. The Sherman crew simply unlatched the large rear access doors. The entire engine was laid out before them, components clearly visible and accessible. The fuel pump was bolted in an obvious location, with clear line connections. They had it swapped with a spare unit in minutes. The contrast was brutal. A German crew might lose a day of combat effectiveness for a repair a Sherman crew could perform during a lunch break. This theme of accessibility extended to every corner of the tank. The electrical system, with its centralized junction boxes, allowed them to trace and replace a faulty wire in a simple, logical process. The gun's recoil mechanism was easier to service. The ammunition was, for the most part, stored in accessible bins, unlike the difficult-to-reach nooks and crannies in German designs. Every single system seemed to have been designed with one overriding question in mind: how can the crew fix this quickly, in the dark, in the mud, while tired and under stress? The impact on crew morale and effectiveness was a variable the German engineers had never properly quantified. A Panther crew lived in a state of constant, low-grade anxiety about their machine. A strange noise, a slight drop in oil pressure, anything could signal a catastrophic failure that would take them out of the fight for days. A Sherman crew, by contrast, operated with a quiet confidence. They knew their vehicle was robust, and they knew that if something did break, they had a fighting chance of fixing it themselves. This confidence translated into aggression and endurance on the battlefield. The final part of the exercise was a mock battle damage assessment. The engineers pointed to a simulated hit on the final drive housing. The German crew's hearts would have sunk. On their tanks, this was a depot-level repair. On the Sherman, they saw the bolted armor cover. They realized that by unbolting this cover, they could access the entire final drive assembly. It was a component that could, in theory, be replaced in the field. The concept was revolutionary to them. Their own tanks were designed as integrated, monolithic units. The Sherman was designed as a collection of serviceable, replaceable modules. As the exercise concluded, the German crewmen stood back, wiping grease from their hands, looking at the Sherman not as an enemy vehicle, but as a tool. It was a tool that respected their time, their labor, and their lives. The engineers' reports from this day were likely filled with a new kind of technical data: time measurements. Track repair, 18 minutes. Road wheel replacement, 27 minutes. Fuel pump swap, 11 minutes. These were not just numbers, they were a damning indictment of their own designs. They had discovered that the Sherman's greatest weapon was not its gun or its armor, but its wrench time. It spent more hours fighting and fewer hours broken, and in a war of attrition, that was an advantage that no amount of superior German optics or armor penetration could overcome. The dissection of the Sherman tank revealed a truth that transcended engineering and struck at the core of the two nations' industrial souls. Germany built tanks in workshops that produced masterpieces. America built tanks on assembly lines that produced victory. This was not a difference in quality, but a chasm in philosophy. The Sherman was the pure product of American mass production culture, a culture the Germans intellectually understood but could never emulate, bound as they were by a tradition of craftsmanship that became a strategic liability in total war. Every component of the Sherman testified to this production line mindset. The Germans noted the extensive use of casting and stamping. Large sections of their hull and the distinctive rounded front of the M4A1 were single cast pieces, reducing the number of complex welds and machining operations. Bolts and fittings were standardized to a degree that seemed almost boring to the German engineers, who were accustomed to custom machined parts for specific applications. This standardization was the language of the assembly line, where speed and interchangeability were the gods to which all else was sacrificed. A Sherman rolling off the line at the Chrysler Detroit Arsenal tank plant was not a unique entity, it was unit number 15,283, identical in every meaningful way to unit number 15,282 and unit number 15,284. This stood in brutal contrast to the German Panzer Zoo. A Tiger tank produced by Henschel and Cassie was not fully identical to one produced later in the same factory, let alone one from a different manufacturer. German production was characterized by constant refinement and modification. While this produced incremental improvements, it murdered standardization. A spare part for Tiger chassis number 250 might not fit Tiger chassis number 280. This was the workshop mentality: each vehicle was a project, a collection of the latest and best ideas, even if those ideas rendered the logistics chain a nightmare. The Americans prioritized consistency. The Germans prioritized perfection, and in doing so, achieved logistical chaos. The German engineers saw the results of this in the very components they laid out on their inspection tables. The Sherman's gearbox was a robust, simple design that could be produced by the thousands by automotive subcontractors. The Tiger's transmission was a complex, precision-engineered marvel that required specialized machine tools and highly skilled fitters, creating a bottleneck that limited the entire production run. The Americans had applied the lessons of Henry Ford to the art of war. The Germans were still operating like guild craftsmen building custom armor for a king. This fundamental divide dictated strategic outcomes. The American system could absorb staggering losses and replace them without a faltering step. A report of 100 Shermans destroyed in a battle was a tactical setback. In Germany, the loss of 100 Tigers was a catastrophic blow to the entire Panzerwaffe, a blow from which it could not quickly recover. The production line could churn out a new tank to replace a lost one in a matter of days. The workshop required weeks. The human element of production was equally telling. To build a Sherman, a worker needed training on a specific, repetitive task. They bolted on the same road wheel, installed the same electrical harness, connected the same fuel line, day after day. This allowed for a massive, scalable workforce, including thousands of women, Rosie the Riveter, who could be quickly trained and deployed. Building a Tiger required a master mechanic, a person with years of experience who could fit, adjust, and troubleshoot complex systems. This was an irreplaceable human resource. Germany was using master jewelers to mass-produce cutlery, while America was using an army of efficient short-order cooks. The German engineers, contemplating the disassembled Sherman, were forced to confront the limits of their own excellence. Their workshop tradition produced tanks that were, in a vacuum, superior fighting machines. But war is not fought in a vacuum. It is fought in a world of mud, scarcity, and attrition. The Sherman was perfectly adapted to this reality. Its simplicity was a deliberate product of its manufacturing origin, a design choice that enabled it to exist in overwhelming numbers. The production line also granted the Americans a hidden strategic advantage: evolutionary improvement. Because the basic design was sound and standardized, they could introduce major upgrades without halting the relentless output of the factories. The transition from the 75mm gun to the 76mm high-velocity gun, or the change from wet to dry ammunition stowage, could be phased in smoothly. A German improvement often required a redesign that effectively created a new vehicle, with a new set of unique spare parts, further fracturing their logistics. In the end, the confrontation at Kummersdorf was between two industrial ages. Germany was fighting a mid-20th century war with a late 19th century industrial mindset. America was fighting with the fully realized power of 20th century mass production. The workshop could produce a better tank. The production line could produce a winning army. The German engineers, surrounded by the elegantly simple components of the Sherman, understood with dawning horror that they had lost the industrial war before the first shell was even fired. Their genius had been expertly applied to the wrong problem. They had built the perfect tank, but America had built the perfect tank system, and in a global war of attrition, the system would always, inevitably, prevail. As the German engineers at Kummersdorf moved from examining major assemblies to the smallest components, they encountered what was perhaps the Sherman's most devastating strategic innovation: its spare parts system. This was not merely a logistical convenience, it was a revolutionary weapon that Germany could not counter. The Americans had weaponized standardization, turning interchangeable parts into a force multiplier that kept their armies moving, while the German war machine gradually seized up from 1,000 small failures. The German experience with spare parts was one of perpetual crisis. Their Panzer Zoo, of different tank models, each with constant minor modifications, created a logistical nightmare. A spare part for Panzer for Ausf. G might not fit an Ausf. H, a component for a Tiger produced in January, might be incompatible with one produced in March. This required maintaining dozens of different part numbers for what was essentially the same function: fuel pumps, water pumps, electrical generators, track links. The system was so complex that frontline units often cannibalized damaged tanks for parts, as requesting the correct component from depots could take weeks, if it arrived at all. The Sherman presented a stunning contrast. The German engineers laid out identical components from different Sherman tanks on their workbenches. They measured, they compared, they tested. A water pump from 1M4A1 fit perfectly onto another, regardless of its production date or factory origin. The bolts were standardized. The gaskets were identical. The electrical connectors were uniform. This was not by accident, it was by design. The Americans had imposed a ruthless discipline on their manufacturing that Germany, with its competing firms and constant design tweaks, had never achieved. This standardization created a logistical simplicity that the German engineers could only envy. An American supply officer in Normandy needed to stock just one type of fuel filter for the entire Sherman fleet. His German counterpart needed to stock multiple types for the Panzer IVs, Panthers, Tigers, and various support vehicles in his sector. This meant the Americans could achieve a density of supply that was impossible for the Germans. A broken Sherman could be fixed quickly because the part was almost certainly available nearby. A broken Panther might wait days for the correct specialized component to arrive from a distant depot. The impact on maintenance capacity was revolutionary. German maintenance units required highly trained specialists familiar with multiple tank models. An American maintenance battalion needed only to master one basic platform. This meant American repair crews could achieve greater proficiency faster, and their repair depots operated with assembly line efficiency. A damaged Sherman would enter a repair depot, and crews would swiftly replace standardized subassemblies, a whole transmission, a final drive unit, an engine, pulled from a vast pool of identical spares. The tank would often return to the front within days, sometimes hours. The Germans documented this with growing alarm. They saw how the Sherman's design enabled module-level repair. Instead of troubleshooting a faulty transmission down to a specific gear, American mechanics would simply swap the entire transmission unit. The defective unit would be shipped to a rear-area depot for proper rebuilding, but the tank was back in action. This philosophy treated time as the most precious resource. German maintenance, by contrast, often involved intricate repairs in the field by master technicians, a process that took far longer and required rarer skills. This parts revolution extended to the tools themselves. The German engineers noted that the Sherman could be almost completely disassembled with a surprisingly small set of standard wrenches, sockets, and screwdrivers. German tanks often required specialized, model-specific tools that might not be available when needed. This simplicity meant that any American crew, even in an isolated position, had a good chance of performing repairs with their basic onboard tool kit. The strategic implications were profound. The U.S. Army could sustain a high operational tempo for weeks on end because its tanks were not just fighting, but were also quickly returning to the fight after damage or breakdown. The German Army, for all its tactical brilliance, operated in a start-stop rhythm dictated by mechanical failures and parts shortages. A panzer division might begin an operation with 150 tanks, but after 2 weeks of hard driving and combat, perhaps only 40 would be operational. A Sherman-equipped armored division in similar conditions might still have 100 or more tanks ready for action. The spare parts revolution also massively reduced the strain on the Allied transportation system. Ships crossing the Atlantic carried pallets of interchangeable parts that could service thousands of tanks. German supply trains were filled with a bewildering variety of specialized components for different vehicles, many of which would never reach the specific tank that needed them. For the German engineers, this was perhaps the most humbling realization. They had always measured military power in terms of armor thickness and gun caliber. But the Sherman demonstrated that true military power resided in something far more mundane, the ability to keep machines running. The Americans had won the war of the spare parts bin before the first tank even rolled onto the transport ship. Germany's technological sophistication had become its Achilles heel, while America's embrace of standardization had become its most devastating weapon, a weapon that kept the Shermans coming, day after day, in numbers and with a reliability that the German army could not match and could not withstand. The ultimate validation of any military vehicle occurs not on the test track, but in the mud, snow, and dust of the battlefield. While the German engineers at Kummersdorf were meticulously documenting the Sherman's technical virtues, a far more damning comparison was unfolding across every front of the war, a comparison measured not in millimeters of armor or muzzle velocity, but in a simple, brutal metric: operational readiness rates. This was the real test, and the data flowing back to German intelligence painted a picture of logistical and mechanical superiority that their own tanks could not hope to match. An operational readiness rate is the percentage of a force's vehicles that are combat ready at any given time. For the German Panzerwaffe, this number was chronically, catastrophically low. A typical panzer division might begin Operation Barbarossa with over 300 tanks. After several weeks of advance, that number could plummet to 30 or 40 operational vehicles, not primarily from enemy action, but from mechanical breakdown. The complex, over-engineered systems of German tanks, the fragile final drives of the Panther, the delicate transmissions of the Tiger, the intricate interleaved road wheels of both, were simply not designed for the sustained punishment of cross-country movement over hundreds of miles. They were garage queens, magnificent in short bursts but incapable of enduring the marathon of modern warfare. The Sherman, by contrast, was a marathon runner. American armored divisions consistently maintained operational readiness rates of 80% or higher, even during intense campaigning. This was not a coincidence, it was the direct result of the design philosophy the German engineers were discovering on their test stands. A tank that can be repaired in hours instead of days, with parts that are readily available and interchangeable, spends more time in the fight. While German recovery teams struggled to tow crippled behemoths back to distant, overwhelmed repair depots, American maintenance battalions were performing near miracles just behind the front lines. The contrast was most stark during rapid advances. In the pursuit across France after the Normandy breakout, Patton's Third Army moved at a blistering pace that would have been logistically impossible for a German force. Sherman's covered dozens of miles a day. When one broke down, and they did, For no machine is perfect, the standard procedure was often to push it off the road, mark its location for the recovery teams, and keep moving. The repair crews, following close behind with their juice-and-a-half trucks filled with standardized spare parts, would have the tank running and back with its unit often within 24 hours. This system created a continuous cycle of combat power. A German Panzer unit in a similar situation faced a very different reality. A single broken-down Tiger could require a company-sized effort to recover, a heavy-duty Farmore half-track to tow, and weeks of work in a specialized depot to repair. During the Ardennes offensive, the mere advance to the starting line caused significant mechanical attrition among the participating German Panzer units. They were already degraded before firing a single shot. The offensive itself then stalled, in large part, because the remaining tanks could not be supplied with fuel and spare parts. Their sophisticated engineering had created a system with no resilience. The environment acted as a merciless amplifier of this disparity. On the Eastern Front, the Russian mud and winter cold crippled German armor. Tanks that were complex to maintain in ideal conditions became impossible to repair in the field. The Sherman, with its robust air-cooled engines, in some models, accessible components, and simpler systems, proved far more resilient to the harsh conditions. Its higher ground clearance also gave it better mobility in mud and snow compared to the lower-slung, heavier German tanks, which were more prone to bogging down. The human factor was equally critical. German mechanics were highly skilled artisans, but there were never enough of them, and the complexity of their task meant repairs took time. The American system was designed for efficiency, not artistry. A damaged Sherman would be descended upon by a team of mechanics, each trained to perform a specific replacement task rapidly. The tank was treated not as a unique masterpiece to be restored, but as a weapon system to be returned to service with maximum speed. This industrial approach to maintenance was a force multiplier that Germany could not replicate. For the German High Command, these operational readiness statistics were a source of constant frustration. They could not understand how the Americans, with their inferior tanks, could sustain such relentless pressure. The answer was now clear to the engineers at Kummersdorf: the Americans were fighting a different war. Germany was focused on winning individual tank duels. America was focused on winning the campaign. A force that can keep 80 out of 100 tanks in the fight will always overwhelm a force that can only keep 30 of its 100 tanks running, regardless of the theoretical superiority of those 30 tanks. The real battlefield test thus delivered a verdict that no amount of tactical genius could overturn. The Sherman's high operational readiness rate was its most devastating quality. It meant that at any given moment, the American armored fist was at nearly full strength. It meant that offensives could be sustained, and defenses could be reinforced without the crippling pauses for mechanical recovery that constantly plagued German operations. The German engineers, confronted with the hard data from the front, were forced to admit a painful truth: their beautifully complex machines were losing the war to a simple, reliable, and endlessly sustainable system. The test track had confirmed what the battlefield had already proven: in modern warfare, availability is more important than ability. The air in the office was thick with the smell of stale coffee, cheap tobacco, and the metallic scent of damp wool. Before Oberst Wilhelm Vogel, the lead engineer of the Panzercommission's evaluation team, lay a stack of papers that felt heavier than armor plate. It was the final draft of the report on the captured M4A1 Sherman. For weeks, his team had dissected, driven, and analyzed the American tank with a meticulous, almost surgical precision. They had approached it with the ingrained arrogance of a school that believed complexity was synonymous with quality. They were now leaving the classroom with a report card that had turned their entire world view on its head. Vogel picked up his pen, its weight familiar in his hand, an instrument he had used to endorse countless blueprints for Germany's feline predators. Now, he had to use it to describe this. He began to write, his script precise and sharp, each word a small battle against his own pride. Subject: Technical evaluation of captured U.S. medium tank M4A1, Sherman. 2. Armaments Ministry, Panzer Development Office. From Oberst Wilhelm Vogel, Engineering Evaluation Group, Kummersdorf. The header was easy. It was the body of the text that felt like a confession. The initial external assessment of the M4, he wrote, confirmed our preconceptions. Its silhouette is tall and box-like, presenting a larger target profile than our designs. The vertical hull faces and rounded cast hull of this particular model lack the sophisticated sloped armor of the Panzer V Panther. Its primary armament, the 75mm M3L 40 gun, is adequate for infantry support and engaging medium tanks at common combat ranges, but is outclassed by the long-range capabilities of the kilowatt K36 and kilowatt K42. He could already hear the readers in Berlin nodding, a chorus of "I told you so." But this is where the report would pivot. This is where the truth began to bleed through the cracks of their technical superiority. However, Fogel underlined the word, pressing down hard enough to slightly tear the paper. A deeper, systemic analysis reveals a design philosophy so fundamentally different from our own that it necessitates a complete re-evaluation of what constitutes an effective weapon system. The Americans have not built a better dueling weapon, they have built a superior war machine. He moved to the section on automotive performance. His mind flashed back to the test track. The frozen ruts of the previous day had turned to thick mud under a sudden thaw. The Panther they had running alongside the Sherman for comparison had quickly begun to struggle, its intricate interleaved road wheels clogging with mud and freezing sludge, its final drive groaning under the stress. The recovery team had been summoned. The Sherman, however, had simply continued. Its wider, simpler tracks distributed the weight more evenly. The reliable, bogus-style suspension, while offering a less smooth ride, did not trap debris. The radial engine, while loud, had not faltered, its torque responding seamlessly to the driver's inputs. The automotive system, Fogel wrote, is a study in robust simplicity. The Continental R975 radial engine, while derivative of an aircraft design, is massively overbuilt for this application. Its power output is consistent and, crucially, accessible across the entire rev range. The transmission, a simple synchromesh system, is intuitive and forgiving. A driver can be trained on it in a matter of days, not months. The steering is managed through a simple but effective controlled differential system, which, while lacking the precision of our triple radius system, is far more durable and requires significantly less physical effort from the driver. In cross-country mobility, especially in adverse conditions, the M4 demonstrated a marked advantage in sustained operational capability. It does not win a sprint on a paved road, but it wins the marathon through the mud of the Eastern Front or the bocage of Normandy. He paused, thinking of the maintenance logs. His team had timed everything. To change a transmission in a Panther was a day-long ordeal, requiring the removal of the turret, a task for a workshop company. They had simulated a power pack failure on the Sherman. The most profound advantage lies in the realm of maintenance and repair, the report continued, the words tasting both bitter and undeniable. The Americans have engineered not just a tank, but a system for keeping tanks in the field. The entire powertrain, engine and transmission, is mounted as a single unit on rails. With a small crane, a crew of 4 can remove and replace this power pack in under 2 hours. We timed it. By contrast, a similar procedure on a Panther requires no less than 16 man-hours under ideal conditions. This is not a minor logistical advantage, it is a tactical and operational multiplier of the highest order. Fogel leaned back, the chair creaking in protest. He looked at the schematics of the Sherman's interior pinned to his wall. It was cramped, yes. But every component was accessible. Filters, electrical junctions, even the notoriously reliable vertical volute spring suspension units could be replaced in the field with basic tools. There were no specialized wrenches, no mystical rituals known only to a handful of factory-trained technicians. The design prioritizes the crew, he wrote, a reluctant admiration seeping into his clinical tone. Every major system is designed for rapid access and replacement. The concept of standardization has been weaponized. The same tools used to maintain a 2.5-ton truck are, in large part, sufficient to perform major surgery on this tank. This creates a logistical footprint that is a fraction of our own. A single German armored division requires a veritable circus of specialized support vehicles and equipment. An American armored division requires a robust supply of spare parts and determined mechanics with standard issue toolkits. He arrived at the conclusion, the part he had been dreading. This was no longer about metallurgy or ballistic coefficients. It was about arithmetic and industrial reality. In conclusion, Fogel wrote, his hand steady now, the fight gone out of him, while the M for Sherman is tactically inferior to our heavy tanks in a one-to-one engagement on open ground, it is operationally and strategically superior in the context of a prolonged, large-scale mechanized war. Its simplicity allows for staggering production rates that we cannot hope to match. Its reliability ensures that a far higher percentage of tanks committed to a battle will actually reach the battlefield, engage, and survive to fight again. Its maintainability means that a damaged tank is not a total loss, but an asset that can be returned to combat in hours or days, not weeks. He took a final, deep breath, the reality of the war crystallizing in this single, damning document. They had been building exquisite, dueling pistols for a knighthood that was already extinct. The Americans were building reliable, easily produced rifles for an army of millions. He signed his name with a final, definitive scratch of the pen. We are not facing a nation with inferior technology. We are facing a nation with a superior system. A system where the design philosophy of reliability, standardization, and ease of maintenance is a weapon in itself. It is a weapon for which we, in our pursuit of the perfect machine, have no effective defense. We have never built, and under our current industrial and philosophical constraints, cannot build, reliability like this. The thunder of the opening artillery barrage, the piercing charge of the infantry, the terrifying spectacle of two steel behemoths trading fire at point-blank range, these are the images that define battle in the popular imagination. They are the tangible, dramatic moments of violence that decide a single field. But the war, the great, sprawling, campaign-consuming monster, was not won by these moments alone. It was won in the silent, grinding spaces between them. It was won by the relentless, unglamorous, and utterly decisive force of operational momentum. And this momentum was generated not by the perfect shot, but by the dependable engine. While German after-action reports and field marshals' memoirs would obsess over the tactical minutiae of tank duels, the slope of the armor, the muzzle velocity of the guns, their Allied counterparts, particularly the Americans, were fixated on a different metric, their operational readiness rate. This was the unspoken advantage, the statistical heartbeat of their armored divisions. It was a number that, in the end, proved more powerful than any single technological marvel. The story of this advantage is not told on the pages of a single, heroic engagement, but across the vast, bloody canvas of entire campaigns. Consider the race across France in the late summer of 1944, following the breakout from Normandy. General George S. Patton's Third Army was a whirlwind, advancing at a pace that bewildered the German high command. This velocity was not merely a product of bold leadership or broken enemy lines, it was a feat of mechanical logistics. Patton's spearhead was comprised of Sherman tanks. Their ability to march day after day, covering 50, 60, even 70 miles without a major breakdown, was what made the race possible. A German panzer division attempting a similar forced march would have been a trail of tragedy. The complex, overstressed engines of the Panthers and Tigers would have succumbed to overheating and mechanical failure. Their delicate final drives would have sheared under the constant strain. The division would have started the march with perhaps 150 tanks. Within 3 days, it would have been a dispersed collection of broken-down machines, strung out for dozens of miles, waiting for the overstretched recovery teams and the rare, specialized spare parts that never seemed to arrive. The advance would have stalled, not from enemy action, but from internal decay. The Sherman, by contrast, just kept going. Its simple, robust engine, while not powerful, was forgiving and durable. Its transmission could withstand the abuse of conscript drivers trained for weeks, not years. When something did break, as something always does in war, the solution was often swift. A company-level maintenance team, armed with standard tools and a replacement part pulled from a truck also used by the artillery or logistics corps, could often have the tank back on the road in hours. This created a constant, rolling force. A Sherman battalion might start the day with 50 tanks. By evening, after a 50-mile road march and a minor skirmish, it might still have 48 or 49 tanks operational. The German battalion, having covered the same ground, might be down to 20. This differential in operational readiness was a force multiplier more potent than any 88mm gun. On paper, a Tiger tank could destroy a dozen Shermans. But in the reality of the Ardennes offensive in December 1944, the question was never one Tiger against a dozen Shermans. It was one Tiger, which had consumed immense resources to even reach the battlefield, low on fuel and ammunition, its crew exhausted from simply wrestling the machine through mechanical gremlins and treacherous roads, facing 3 or 4 Shermans that had just driven up a reliable highway, were fully fueled, and were being followed by a steady stream of identically supplied replacements. The American industrial and logistical system did not just produce tanks, it produced availability. A damaged Sherman, recovered from the battlefield, was not a total loss to be hauled back to a distant factory in Germany. It was a candidate for repair. Field workshops, or even larger depot facilities established just behind the front lines, acted as mechanical triage centers. A tank with a blown-off turret might be cannibalized for parts. A tank with a damaged engine would have its entire power pack swapped out in a matter of hours. These repaired tanks would then re-enter the logistical stream, flowing back to the front to fill the gaps. It was a circulatory system that kept the army alive and fighting. The German system, by contrast, was one of catastrophic failure. A disabled Panther was often a permanent loss. The lack of standardization meant spare parts were scarce. The complexity of repairs often meant the tank had to be shipped all the way back to the Reich. The journey was long, vulnerable to air attack, and the tank was almost never seen again at the front. This attritional drain was constant and insidious. They were not just losing tanks to enemy fire, they were losing them to the very philosophy that had created them. The ultimate expression of this unspoken advantage was in the sheer, crushing weight of numbers that could be sustained at the front. By the end of 1944, the Allies weren't just winning because they had more tanks in total, they were winning because they could consistently field more tanks every single day of the campaign. A German panzer division might be at 20% of its strength, its remaining tanks hobbled and awaiting parts. The American armored division facing it would be at 80% or 90%, its crews rested, its tanks refitted, and its supply lines full of fresh vehicles and replacement parts. This was how reliability won campaigns. It won the race across France. It weathered the storm in the Ardennes. It forged the relentless advance into the heart of Germany. The war was not a series of static duels, but a fluid, dynamic contest of movement and supply. The Sherman, for all its documented flaws in a direct firefight, was the perfect instrument for this kind of war. It was a tool of operational art, not just tactical prowess. Its ability to be there, to be ready, to be fixed, and to be replaced, created a tidal wave of pressure that no amount of German tactical genius could permanently hold back. The unspoken truth of the Western Front was that the most powerful weapon was not the one that could destroy a single enemy in a spectacular blast, but the one that could reliably roll onto the next objective, and the next, until the enemy had nothing left with which to fight. The final, reluctant admission from the engineers at Kummersdorf did not, and could not, alter the fate of the Third Reich. The report by Oberst Vogel and his team was likely filed away, a whisper of inconvenient truth drowned out by the crashing symphony of a collapsing regime. The war was lost not in a single tank-to-tank duel, but in the relentless, grinding arithmetic of production, logistics, and operational readiness that the Sherman embodied. Yet, the legacy of this evaluation, and the brutal lessons of the war itself, would echo for decades, forcing a fundamental and painful re-evaluation of what truly constituted the perfect tank. In the immediate post-war world, the victors, the Soviet Union, the United States, and Great Britain, each absorbed the lessons of the armored conflict through their own ideological and doctrinal lenses. The Soviet Union, whose T-34 shared the Sherman's philosophy of simplicity, mass production, and reliability, doubled down on this path. Their Cold War-era tanks, from the T-54-55 to the T-72, became the new global standard for a balanced, effective, and prolific main battle tank. They were not the most technologically sophisticated, nor the most comfortable for their crews, but they were numerous, mechanically robust, and designed for the harsh realities of large-scale warfare. They were, in essence, the spiritual successors to the Sherman, a testament to a doctrine that valued the ability to field and sustain a massive armored force. The United States, ironically, initially strayed from its own winning formula. Seduced by the terrifying spectacle of the German big cats and facing the new Soviet armored hordes, the U.S. Army entered the Cold War with a bigger is better mentality. Tanks like the M103 heavy tank were direct descendants of the Tiger, immensely powerful, heavily armored, complex, and built in limited numbers. They were designed for the single, apocalyptic duel on the plains of Europe. For a time, it seemed the American military had forgotten its own greatest lesson, that wars are won by machines that work, not just by machines that win theoretical engagements. This period of amnesia, however, was corrected by the crucible of real-world conflict. The wars in Korea and Vietnam were not vast, set-piece battles across the North German plain. They were conflicts of limited infrastructure, long supply lines, and harsh environments. The complex, fuel-guzzling behemoths of the immediate post-war era proved ill-suited to these challenges. The U.S. military rediscovered the virtues of strategic mobility, tactical flexibility, and, above all, reliability. This reawakening culminated in the M1 Abrams. The M1 Abrams is, in many ways, the ultimate synthesis of the lessons learned from the Sherman and its German adversaries. It possesses the raw power and protective qualities of a Panther or Tiger, with a fearsome main gun and advanced composite armor. Yet, its soul is that of the Sherman. Its core design principle is maintainability and reliability. The AGT 1500 gas turbine engine, for all its complexity, is housed as a single, removable power pack, allowing for replacement in under an hour, a direct inheritance from the Sherman's design genius. Its extensive use of modular components and a philosophy of line-replaceable units ensures that damaged tanks can be returned to service with breathtaking speed. The Abrams is not just a powerful weapon, it is a sustainable one, designed to be kept in the fight by a logistics system that understands availability is the ultimate currency of combat. The German school of engineering, humbled by defeat, also evolved. The new Bundeswehr of the Cold War could no longer afford to build handcrafted masterpieces. The Leopard 1, and later the superb Leopard 2, represented a new, more balanced philosophy. They retained the German penchant for excellent optics, fine engineering, and superb fire control systems, but they were designed with reliability, maintainability, and interoperability with NATO allies in mind. The Leopard 2, like the Abrams, features a modular power pack and a design that prioritizes strategic and tactical sustainability. The ghost of Kummersdorf had finally been laid to rest. The pursuit of quality was no longer at odds with the necessity of quantity and dependability. The true legacy of the Sherman, therefore, is not in its physical form, but in the paradigm it forced upon the world. It shattered the myth of their perfect tank as a singular, unbeatable dueling machine. It proved that the perfect tank is a relative concept, defined not by a spreadsheet of its technical specifications, but by its role within a larger military, industrial, and strategic ecosystem. A perfect tank is one that can be produced in the thousands, not the hundreds. A perfect tank is one that can travel 100 miles to a battle without breaking down. A perfect tank is one that, when damaged, can be repaired by its crew or a field workshop with standard tools, not shipped back to a factory. A perfect tank is one that can be consistently supplied with fuel, ammunition, and spare parts across vast distances. A perfect tank is, ultimately, one that is there, on the battlefield, operational, when it is needed. The German engineers who tested the captured Sherman were forced to confront a truth that transcended their technical analysis. They saw that the Americans had weaponized an entire system, from the factory floor to the frontline mechanic's toolbox. The tank was merely the most visible component of this system. The real defeat was not of their engineering prowess, but of their strategic philosophy. The legacy of the Sherman is the understanding that in modern warfare, the whole is infinitely greater than the sum of its parts. Their perfect tank is not the one that wins the duel, but the one that wins the war. It is a lesson written not in the flash of a main gun, but in the relentless, grinding, victorious momentum of an army whose machines simply, reliably, and unforgettably work.